3 and 8. 3.125. Everybody able to get Ferry's voltage? If I wanted to be ignored, I could have stayed home.
Yes.
Yes, sir.
Okay, thank you for replying to me somehow. Now tell me if there was resistance. Take R1, multiply it times R2, and divide that by 32,000.
Can you just do 22 times 10?
10,000. Enter, divided by 32,000. What do you get for Thevenin's resistance? Anybody get that number?
Yeah.
How come you don't talk to me?
I'm right. Wrong.
6.875K,
Yeah. Just do
and lo and behold, sure enough, the textbook is rounded, Kevin. And it says 6.88K in the book.
To the hundredth place.
Well, I'll leave it right here to 1,000 bucks, okay? Those are the two numbers that you use, and you got to solve first. Take these two numbers and plug it in right here, and find the emitter current. First thing, so you'll know what this current right here is. Wait somebody to tell me what the emitter current is.
Wait, what do we do next?
You're finding the emitter current.
IE.
Well, that's IE, yes, IE. There's adding going on in the denominator. Put parentheses around the entire denominator. Or somebody you'll make a mistake.
Where'd you get the VVE?
Sir?
Where'd you get the VVE?
The V what?
Yeah, never mind, I got it.
VEE, that's the emitter voltage
Yeah,
for the T and P circuit.
Jennifer helped me out. I realized it. It was a dumb question.
No, it won't. There's no such thing as a dumb question.
I didn't think it all the way through.
It's a question that you're inquisitive about. And that's how you learn. Ask questions.
Yeah, I see.
That's what I'm here for. We come up with the emitter current, somebody. What is it? 2.31 milliamp. And notice that's the same current in the book. But what did it have in the book?
Oh, look. Oh, there's
Negative. We got a negative 2.31 because it's a P and P circuit. Okay, now that I got the emitter current, now the game is on. The very first thing you do now, the voltage across the emitter resistor, which is the emitter voltage. And voltage is what? Voltage is equal to current times resistance. So what is the voltage at the emitter terminal? If I was to take a voltmeter and measure from ground at the emitter terminal, am I not looking at the voltage across the emitter resistor? And that'd be 2.31 volts, wouldn't it? Richard, are you talking to me, sir?
No, I'm agreeing.
You agreeing, or you just don't know? Or I don't know, be a yes man. You know what a yes man is, right?
It's a yes, whatever you say.
Argue with me. Push me in a corner. That might be why you passed the test.
I'm agreeing.
Although with you, you're doing fine, sir. I'm picking on you. But challenge me. Don't be a yes man.
So
What is the voltage at the emitter? Voltage is current times resistance. So 2.31 times 1,000.
Comes out to be
2.31 milliamps times
Milliamps,
1,000. I know that's going to be 2.31 volts. when I multiply a number times 1,000, it cancels out the milli. Well, milli is 1,000th, isn't it?
Oh, yeah.
That's how I knew it was 2.31 volts from my head. So guess what goes right there? 2.31 volts.
Yeah, if you didn't put the milli, then you'd still be the same thing you got before.
No, when I multiplied that
No,
2.31
I'm
milliamp times 1,000, that 1,000 cancels out the milli.
Yeah, but I didn't, I just did it.
And I just say 2.31 volts. So you're looking at textbook, what does it say about the emitter current? And what does it say about the emitter voltage? Oh, in this case, it won't be right, because it's a piece of it. So now it's different than the book. Don't worry about that. Everybody see how I got the emitter voltage? Okay. Well, because this is true, you now know to emit the collector current. And that's going to be about 2.31 milliamp. Because with a voltage by the circuit, the emitter current, the collector current is pretty much the same thing.
So it's 5.
So now I can calculate the voltage across the collector resistor. Because voltage is equal to current times resistance.
So 5.08 milliamp.
No, voltage is not measured in milliamps. Take that number right there.
That's 2,200.
That's 0.00231 times 2,200.
5.082.
0.00231, yeah, that's right. 2.31 milliamps. So, can anybody tell me the voltage across the collector resistor?
5.082.
So you're talking to that old man, holler.
5.082 volts.
Okay, let me make sure you're right.
Yeah.
0.00231 times 2,200. And that gives me 5.082. Right, is what you still?
Mm-hmm.
Okay, so I know the voltage across the collector resistor. So therefore, find that goes right here, don't it? The voltage across the collector resistor. So that's going to be 5.082.
How did you do that?
5.082 volts. If I see how I found a voltage across the collector resistor, Ohm's law.
It's current times resistance, right?
Current times resistance is always voltage. I knew the current. I knew the resistance. So I calculated the voltage across that resistor. And that's the voltage from there to there. Okay, looky. If you know that voltage right there to be, what was it, 5.082?
Yep.
And you found this voltage down here to be 2.31. Can you tell me the voltage from there to there?
7.
Take the 10, subtract that number from it, and then subtract that number from it. And what's left over has got to be the voltage at the collector measured from the emitter.
2.608.
I don't know.
Yeah.
So I'll take 10 and subtract from it. The reason I take 10 is because that's my supply voltage. Then I'll subtract that voltage right there from it. So that'd be 5.082. Then I'll subtract that voltage from it, because that voltage is across that resistor, 2.31. And what's left over is got to be across the transistor of 2.608. This voltage right here is 2.608 volts. That's an O. So the voltage at the collector measured from the emitter, the voltage at the collector measured from the emitter is 2.608 volts.
What do you?
Well, I see how I found that voltage.
Can you do that one more time? I'm sorry.
I know, Aiken, that voltage plus that voltage plus that voltage is going to add up to 10.
If you know this voltage and that
So I took my 10, subtracted that from it, and I subtracted that from it. What's left over has got to be that right there. Kirchhoff's voltage law never lies. John? if I took a voltmeter and measured from ground the voltage at the collector terminal, wouldn't it be that voltage right there sitting on top of that voltage right there? So the voltage at the collector terminal is going to be the sum of that number and that number. So I add these two numbers together, and that'd be the voltage measured at the collector.
2.918.
So I'll go 2.608, is that it?
Yep.
Plus 2.31,
4.9.
and that gives me 4.9. I'm going to call it 4.9. Did I do something wrong?
Oh, no, I was like, yeah, I was
I've done many things wrong. We hit 2.90. I'm gonna call it 2.92.
What's
Okay?
he finding right now?
2.92. So the voltage at the collector,
Voltage from the collector in relationship to
4.9.
So
4.9
across the
to
resistor plus the voltage across the emitter resistor.
4.92
Right.
volts.
Was that the two?
That's the voltage I would measure at the collector with a voltmeter,
2.31.
which would be 2.6 on top of 2.3. That voltage right there is sitting on top of that voltage right there. So the voltage right there should be that plus that. Kirchhoff voltage law. Voltages in series add. Okay, what would be the voltage at the collector measured from the base terminal? Oh, first off, before we do that, what is the voltage at the base measured from the emitter?
0.7.
What is, if I took a voltmeter and went from there to there, the voltage at the base measured from the emitter, what would it be?
0.7.
Thank you, 0.7 volts. So right there, the voltage at the base of the emitter is 0.7.
So then that'll be DC.
All right. Now, if this from here to here is 0.7, and from here to here is 2.6, then the voltage here to here must be 2.6 minus 0.7. So I'll take that 2.6 and subtract 0.7 from it, and that'll be the voltage at the collector measured from the base.
1.908.
So I go 2.608, 2.608 minus 0.7, and that gives me 1.9 volts.
And 2.6
The voltage right here from there to there is 1.9 volts. I mean, that voltage plus that voltage got to add up to be that voltage, don't it? That voltage is on top of that voltage. So 1.9 plus 0.7 got to add up to be 2.6. So I'll right over here where it says voltage at the collector measured from the base would be 1.9 volts. All I'm using here is Ohm's law and Kirchhoff's law. Only two, I'm jerking them around to my advantage, using them how I would see fit. And those are the only two rules I'm using. Ohm's law and Kirchhoff's voltage law. What's the voltage sitting across R2? Wouldn't it be 2.3 plus 0.7?
Because it's parallel.
No, that voltage right there is in series with that voltage right there. So the voltage across R2 is going to be 0.7 plus 2.31.
So 3 volts.
Okay,
And then
so
7
just take
across R1.
2.31 and add 0.7 to it.
3.01.
3, sir, plus 0.7. 3.01, I'll call it 3 volts. 3.01, 3 volts. So the voltage across R2, 3 volts.
And 7 volts across R1.
Now, wouldn't that be the voltage at the base? If I took a voltmeter and measured from ground the voltage at the base terminal, wouldn't I be looking at that 3 volts across R2?
Mm-hmm.
So the voltage at the base is 3 volts.
So 2.31 plus 0.7.
2 point, yes sir.
Voltage at the
Yes
emitter.
sir, yes sir. 2.31 plus 0.7 is the voltage at the base. What about the voltage across R1? What would that be?
7.
Once you take 10 volts to subtract that number from it, what you got left over? 7? Hey, here I got 7 volts sitting on top of 3 volts. That voltage plus that voltage, but add up to 10. Using Kirchhoff's voltage law again. Every opportunity I can see, I'll pick it. So the voltage across R1 is 7 volts. The saturation current.
You said you just subtract 10 from 3. 10.
So what?
So 10 minus 3, 7 volts.
Yeah.
Okay.
A 10 minus 7 will gave you, or 10 minus 3 gave you 7. I know Aiken, that voltage plus that voltage got to add it to be 10. Because they're in series with each other, aren't they?
All right.
Okay. I can tell you right now that it's still. How I know? The voltage at the base right here, 3 volts, is really close to Thevenin's voltage. So I can pretty well bet that it's still. And we're going to check it out in just a moment. First, now I want you to tell me what the saturation curve is. Now, when it's saturated, the transistor is fully turned on. The current's maximum, right?
Yeah.
So this is what you can do. Just put a dead short between there and there. That will represent the transistor that's fully turned on. Dead short, okay? Current's maximum to it, okay? So now you can calculate current, saturate is equal to 10 volts divided by the resistance that's in the way. That's going to be 2,200 plus 1,000.
So 3,200.
That'll be 3,200. So 10 divided by 3,200. And that'll be my saturation current.
3.12 again?
Let me see. 10 calculator keeps going. 10 divided by, what did I say, 3,200? And that's going to be 3 1/4. Not a quarter, 3 1/8.
What's the 10 that we have?
3.125 milliamp. Now, we got 2.31 milliamps going through it. So it's not fully turned on. If it's fully turned on, the current would be that number right there. But it's not fully turned on. It's like a water spigot that's not fully turned on, the flow's not maximum. But it's close to being turned on. Okay. Now, I'll get to that right here in just a moment. Now, let's calculate little R prime E. Take 0.025 and divide it by the emitter current. And the emitter current was 2.31 milliamp. So we divide millis by millis, you can just throw the millis away.
10.8.
So I go 25 divided by 2.31. That should be about 12. So what do you get?
0.025
No,
divided by
that's not right.
2.31.
No.
Yeah. 10.8. Where you get
Looky. 25 millivolts, so that's 25. E negative 3. That's 25 millis. Divided by the emitter current, 2.31 E negative 3. We divide E negative 3 by E negative 3. E negative 3 will go in E negative 3 one time. So I can throw the millis away.
Is 25 millivolts a given?
So what?
Is 25 millivolts?
That's a given.
Okay. So
It comes from the Shockley equation,
Okay.
which is in the back of the book, and it involves calculus to calculate that.
And that is.
So they gave it to you. So 25 millivolts divided by the emitter current. So that's going to be 25 divided by 2.31.
It's 10.8.
2.31, and that's about 10.8 ohms. So where the hell did it go? I got a 10.8 ohm. It's gonna be a low resistance. Okay, now let's calculate the base current. Oh, we don't know the orient at the base yet. And put a spot for this. Why didn't I do that? I did put it there, did I? I got 10 minutes, don't worry, we're gonna finish. I think. I meant to put this up there too, it's the orient base. Is equal to the voltage at the base times beta divided by the emitter current. So I got all these numbers, the voltage at the base. Find it. Voltage at the base is 3 volts. So that number right there is 3. Multiply it times 150. So 3 times 150. And divide that 450 by the emitter current, which is 2.31 milliamps. And that's 0.00231. And that gives me 194.8 K. minutes. 194.8 K ohm. That's almost 200,000.
That's the wrong spot. Yeah.
94 point, say what?
You put it under the. Sorry.
Going too fast.
Oh, right here on it. Ah, thank you, Jennifer, you're helping me. 194.8 K ohm. That's the orient at the base. That's how much resistance it's got looking into it. That's why it didn't drop that base voltage very much. It did drop it 1/8 of a volt. Voltage at the base is 3. The finished voltage is 3 1/8. So it didn't drop it much. And the reason it didn't drop it much, because when I connected it up to that point right there, all this right here looks like a 200,000 ohm resistor. So it didn't upset it very much. Now, I asked a question.
It's 15.4 million.
What is 10 times bigger than 10K?
100K.
Is that bigger than 100K?
Yes, it is.
Stiff. See how easy that is to do? You just ask yourself the question. Is Rn at the base 10 times bigger than R2? Or 4? 10 times R2 is 100K. And Rn at the base is greater than 100K. So it's stiff. So you come over here, and yes, that sucker's stiff. Is that how it works? Now, we got 5 minutes to do the load line.
You're doing voltage base over rise over.
Oh yeah, take the voltage at the base divided by Rn at the base. The voltage at the base was 3 volts, and divided by that 190 some K.
So the
And let
15.4.
me do that. That's 3 divided by 194.8 thousand. 194.83. And that's going to give me 15.4 microamps. Told you it's going to be tiny.
That's what the IB.
That's the base current. 15.4 microamp. Very, very tiny. Now, this is how you draw the load line. Well, you got 10 volts for the source voltage. So you mark out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Call that point right there 10. So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7, that's 8, that's 9. And this is the voltage that the collector measures from the emitter. And when the transistor is fully turned on, that's saturated in it. And the saturation current was 3 1/8 milliamp. So right here, I'm gonna declare that point right there, 3.125 milliamp. So if that's 3, maybe that's 2, and maybe that's 1. There's 2 milliamp maybe, and that's 1 milliamp. Okay? You draw the load line from the saturation point to the cutoff point. Just like that right there. There's your load line. Where on that load line am I idling at? Well, the voltage at the collector measured from the emitter is 2.6 volts. So the voltage at the collector measured from the emitter, what did I say? 2.6? So 1, 2, that's going to be somewhere about right there. Right there is 2.6. And the emitter current is 2.31 milliamps. So that should correspond to about 2.31 milliamps right there. 2.31 milliamps. So there I am on the load line right there. And I want you to identify that point as key point. That's what I had on the load line. I'm not fully saturated, but I told you I was close. I got 2 minutes. Well, I did a complete worksheet for you right there. All the equations are on the worksheet. Eventually you get to the point where you won't need them, I hope. That's what I'm counting on. Let me put my cap to my red pen. Okay, Jesse, what you do with it? Well, I'm trying to try it out.